Okay, number 15. What is the force on a charge located here if the charge Q is 2 microcoulombs? So let's take a look at this. So you got 2.05 microcoulombs here. You got 4.1 microcoulombs here because it's 2 times that. And we'll put a minus sign on it, and then 2.05 here. So divide and conquer here. This is at 3 centimeters. This middle one is at 8 centimeters. So the separation between these is 5 centimeters. So you're going to do Q1, 2 microcoulombs, Q2, minus 4 microcoulombs, divided by 5 centimeters squared. Put that on Wolfram alpha. That'll be the force. This guy is going to be attracted towards that one. And then this one, this is closer. So you're going to have the same force, but instead of 5 centimeters, the difference is 8 to 11 centimeters. So that's going to be 3 centimeters squared. So you can put 3 in there, you're going to get a bigger force. And then the force here, let's call it F2 minus F1 is going to be F net, your net force. And then the question is, what's the force? And that's what it is. So you get your F1 this way, your F1 that way. They're unbalanced. Subtract the difference, and then that'll be the amount left over that's going to be attracted towards it. Okay, delete screenshot. Okay, number 16, consider the figure. We've got a symmetrical arrangement in which the top 2 charges are plus 7 microcoulombs, the bottom 2 charges are minus 7 microcoulombs, and the middle charge Q is positive. Using the symmetry of the arrangement, determine the direction of the electric force on charge Q. So let's go to here. So Q is positive in the middle, QA is positive, QB is positive, QC and D are negative, but the same magnitude. So from QA, it's going to be repelled. From QB, it's going to be repelled. From QD, it's going to be attracted, and QC is going to be attracted. When you add up all those components together, you get a net force down, so it should be straight down. If you look at each of these vectors independently, you've got an x component and a y component and an x component and a y component. The x components cancel each other out, so you're only left with the y components down. Okay, so that's that. For calculating the magnitude of the force on the charge, they're telling you that this is 11.2 centimeters on a side, and that the charge in the middle is 2.45 microcoulombs. Okay, so what you need to do to figure out QA is you need to know the distance here, and so this is going to be 11.2 divided by 2 is that distance, and that's the same as this distance. So this distance is the distance square root of 2 times 11.2 squared. 11.2 squared plus 11.2 squared is going to be, and then square root that is going to be the length of this, and then the force here, force there is going to be K Q1 Q2 over this distance r squared. And so that force is going to be equal to this plus 7.15 microcoulombs and this 2.45 microcoulombs. You're going to put that in there and get this force here. Now, QB is the exact same force, so you don't have to recalculate it. And QC and D are the exact same force. You don't have to recalculate because they all have 7.15 microcoulombs. So then what you need to do, though, is recognize if we just look at this one force, QA, what we care about is that component of it. And we know that this is a 45-degree angle because it splits this right in half. So if we do adjacent over the hypotenuse there, if we take our hypotenuse, which is F, so F cosine of 45 degrees is going to be the y component here down. And the magnitude of the force is just going to be 4 times that because we've got 4 forces all working together in that same way, in that same angle. And so that's how you calculate the magnitude there. Delete. Okay, number 17. Common transparent tape becomes charged when you pull from a dispenser. If one piece is placed above another, the repulsive force can be great enough to support the piece's weight. So you rip off 2 pieces, they have the same charge, they separate each other. You got 14 milligram piece of tape. What's the magnitude of charge on them? So what we have here is one piece of tape, another piece of tape. We've got, if we look at the force diagram on one of these pieces, it should have the weight down and the force of the electric force balanced out. So the sum of the forces should be Fe plus the weight should be ma, the acceleration, and it should be 0 since we're in balance. So the electric force should be equal and opposite to the weight, mg. And so the electric force is kq squared over r squared is equal to mg. Since they both have the same charge, you can just have it as q squared. So then q is going to be the square root of whatever this algebra gets you. Okay, delete that screenshot. 18 here, an electron and a proton are fixed separation 927 nanometers. Find the magnitude direction of the electric field at their midpoint. Okay, so you've got a plus and a minus. They're separated. Halfway between them, what's the magnitude and direction of the electric field? You've got a plus charge and a minus charge, and you've got a distance between them of 927 nanometers. Okay, halfway between there, you can just divide this separation by 2, and you know that the electron and the proton, the proton's electric field is going to be this way, the electron's is going to be that way. So at the center, they're both going to add together, and you're going to get an electric field. You know, the electric fields of all these look like that. So right at the center, you're going to have them combining and adding together. So what's the magnitude and direction? Remember, the electric field is kq over r squared. And so we get this over 2 is our r, and then we use the charge on the electron for the electric field strength for the electron, or the q for the proton, and figure that out. So then the total electric field, E total, is going to be kq over r squared, charge on electron, plus kq proton over r squared. And since the charge on electron, charge of the proton, the electric field is going to be in the same direction, then the total is just going to be 2kq over r squared. And then that should be your electric field. 19. Electrons located at the x-axis. At this location, find the magnitude direction of the electric field at x equals 2.5, 3 times 10 to the minus 6, do the same electron. So we've got an electron here, there's 0, so we're at minus 9.85 times 10 to the minus 6 meters there, and they want to know where is it over here at 2.53 times 10 to the minus 6. So you want to add these two together, take this as a plus number because you want the total distance here for your r, and then it's just kq over r squared, and the trick is getting that r there. And then the direction, remember the electric field goes into an electron, so for the direction of the electron, the electric field, make sure you have that. Okay, 20. A small plastic ball has a charge of 1.95 coulombs, is suspended by a string that has a length of 1 meter in a uniform electric field, as shown in the figure. If the ball is in equilibrium and the string makes 9.8 degrees, what is the electric field strength? So this is going to maybe be the hardest problem for you. The charge here is going to experience a force that way. The force here has a magnitude of Q times E. That's it. There's also a force down here, the weight of the charge of the ball, 2.25 grams, mg. Those forces are balanced, because this thing is just hanging there at 9.8 degrees, by this tension force. So we know that the tension force is going to be split up into an x component and a y component, and the x component of the tension is going to be this way, and this x component should balance out that x component, so I should draw them as the same length. This y component of the tension should balance out that y component. So Tx should equal to Qe, and Ty should equal to Mg. And, T then, if this is your angle, and that's T, the hypotenuse, if you want Ty, which we can also draw here, then that's going to be adjacent over hypotenuse. So you're going to have T cosine theta is equal to Qe, and T sine theta is equal to Mg. And what we want to know is E, electric field strength. Okay, so we got to figure out T. T is equal to Mg over sine theta. And so then we can plug that back in for T up here. We get Mg cosine theta over sine theta. You know what that is, sine over cosine. And then is equal to QE. And then you can just solve for E. So Mg over Q times this blah 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 gives you your electric field strength. And then the cosine of theta and the sine of theta are because you're taking the y component and the x component, and your angle here is 9.8 degrees. Okay, delete that. Newton's laws. All right, 21. Consider the symmetrically arranged charges in the figure. you've got A and B minus 3 and C and D plus 3. So this is the exact problem we already did, but in terms of, instead of finding the force F, we're going to determine the force, the strength of the electric field E. So you're going to do the same thing. You've got charge here. Remember, electric field, you can ignore this charge because we divide it out. So this is kq over r squared. So at this point here, the electric field due to point A, since A is negative, the electric field should be pointed towards A at this point, and towards B at that point, and away from C at this point, and away from D at that point. So the net electric field should be up, and then you'll do the same thing. You figure out one of them, you find the component, the cosine of it, because there's your 45 degree, and you multiply by 4, since they're all adding up in the same direction. So that problem seems like it might take a while and be hard, but it's very simple. 22, you got capacitors, 2 plates of area 499 centimeters squared. And so the capacitance is epsilon naught, which you can type into Wolfram alpha as epsilon naught, or the other way is electric constant, and epsilon naught A over D. That's it. So we've got 499 centimeters squared divided by 42.1 centimeters times this electric constant. All right, and that gives you the capacitance. Consider 2 capacitors. You've got 10.9 and the other. The 2 capacitors are connected in series with a voltage of 325. And the question is, what's the capacitance of the other one? So we've got 2 capacitors in series. Okay, so these represent the parallel plate of the parallel plate capacitors. Those are the plates. So your electricity is flowing through the 2 components. What you know when they're in series is they all have the same charge. So delete all this. So the 2 capacitors are connected in series with a voltage of 325 volts across the capacitors. As a result, the unknown capacitor has a charge of 1.21 millicoulombs. So you know that the other, so C1 here is 10.9 microcoulombs, and this one is C2. We don't know what it is, but we know they have the same charge, 1.21 millicoulombs and 1.21 millicoulombs, because that's just a rule when they're in series. But they have different voltages, V1 and V2. But we know the total voltage is 325 volts across all of them. So what we can do is say that Q is equal to CV, and the charge of 1.21 millicoulombs is equal to C times V. So if we take Q over C, 1 V1, then we can get C1, and we can figure out what V1 is. V1 is going to be Q over C1, and then V total minus V1 is going to be equal to V2. V2, now we have the voltage on this charge, this capacitor, and the question is, what's the capacitance? So we have the same Q, we're going to have C2, which we want to know, and then V2, we solve from up here, so C2 is going to be Q over V2, and then we're done. Okay, delete that. 24. Suppose when a charge Q is moved across a potential difference of delta V, the change in potential energy is given by PE initial. So we've got a some potential difference here, and we take a charge and we move it across to here. So the total energy there is potential energy. We just call it PE initial. What will the change be, though, if for the same potential difference we multiply it by 3? So the potential energy is equal to Q D, the distance, QED. And when you have that, if you multiply the, if for the same potential energy here, you get, oops, hold on, let me open this guy up and make sure I'm in the right section. Okay, so so the potential energy is QED, and then that's also equal to Q times the voltage V, whatever that is, the potential difference. So for the same potential, we multiply the charge by 3. So if we multiply the charge by 3, in order to balance that equation, we're going to have 3PE is equal to 3Q ED in order to make the equation match. So all we end up with is 3 times the initial energy. And what will the change be if the charge is multiplied by 3 still, but now the potential difference is also multiplied by 3? So that means we increase the voltage by 3. So we've done one version of 3 and another version of 3, so we're going to increase the total potential by 3 times 3, and that should be that 9 there. Okay, delete screenshot. All right, number 25. So the change in electric potential energy can be calculated using change of PE equals QV. This is the charge, blah, blah, blah. Rank the change in electric potential energies for the situations described from lowest to highest. So you're supposed to drag these up into the picture with your mouse or whatever. So I'd say just grab this first one and drop it in there. And it says you got a charge Q over 4 moving through a potential VC over 4. Okay, since we know that they're proportional Q and V to each other, then if you have the full Q and the same VC over 4, well, this one better have more of it because it's bigger than Q over 4. And then this one's Q over C, Q over VC, so this C isn't divided by anything, that Q isn't divided by anything, so this is higher yet still, so this one should be, so you can put that one here, put this one above it, put this one above it, and then do the same algorithm and figure out where these other two sit. Okay, 26. 4 capacitors arranged in the circuit shown. You've got C1, C2, C3, C4. What is the equivalent capacitance of the circuit? So you can just figure out the total capacitance here. And this is just C3 plus C4. And then the total capacitance here is 1 over C total is 1 over C1 plus 1 over C2 plus 1 over C3. So you're going to calculate what this is and take 1 over it to get your total capacitance for the whole circuit. Then the question is, what is the charge on capacitor 2? And the charge on capacitor 2, which is here, we've got the voltage of 21.5 volts. And you can figure out what the total charge is on the whole circuit by saying Q is equal to CV and C total times V total. And that charge will be the same on C1, C2, and C3 plus C4. The combination of them. Okay, so the Q then is just going to be the capacitor total capacitance divided by, or times the total voltage. So we got 21.5 volts times our total capacitance here. And then what is the potential difference across capacitor 3? And so then what you have to do is remember that you're going to have V1 here, V2 here, and then both of these are going to have V3 and V3 are going to be the same voltage on each of those things. So what you want to do is figure out what the voltage, if you got 21.5 volts there, you can figure out what the voltage is here, you can figure out what the voltage is here, because Q equals CV, and Q is C1 V1, and Q is C2 V2. And so then you can figure out what V1 is and what V2 are from those equations, since we know what C1 and C2 are. So then 21.5 volts minus V1 minus V2 should be equal to V3. And then once you figure that out, you can get your voltage here. And then what is the potential energy stored in capacitor C4? And then you know that the voltage there is the same as on C3. So once you figure out V3, you can do the energy is 1/2 C4V squared, 1/2 CV squared, and calculate what that is. Okay. And then 26. 26, hello. Oh, okay, that was 26. Okay, 27. What is the maximum number of 7 microfarad capacitors can be connected in parallel with a 4-volt battery while keeping the total charge stored within the capacitor array under 381 microcoulombs? Okay, so they're asking in parallel. So you're going to hook a lot of capacitors in parallel like that. So that means you've ganged all the ends together and here, right? So if you remember, the total capacitance for this is just C1 plus C2 plus C3. So you're going to have n number of capacitors to be your capacitance. And so the total charge is going to equal the total capacitance times the voltage. And the total capacitance is going to be n times 7 microfarad farads times 4 volts, and that has to be limited to this charge, 381 microcoulombs. So you can solve for n to figure out how many of these can add up to that. And then that just gives you the number, okay? But this is learning the parallel series difference. And then if the same number of 7 microfarad capacitors are connected in series within the same 4-volt battery, how much charge will build up on each capacitor plate? So now we, instead of doing that, we add our capacitors up in series, okay? And so we put the same number, so let's say this was 10, and so we're going to have 10, 1, 2, 3, 4 to 10 in series. How much charge will build up on each capacitor plate? So now what we have to figure out is we're going to have 1 over C1 plus 1 over C2 plus 1 over blah, blah, blah to get our total capacitance. But since they're all the same, it's just going to be N over C because 1/2 plus 1/2 plus 1/2 is the same as 3 halves. So you just have N over C, and that's going to be 1 over C total. So solve for what C total is, and then Q is CV. You can figure out what the charge will be on each of those, and they will each have charge Q, even though the voltage is different across each one. So if you find the whole thing, the total voltage, the total charge, the total Q and capacitance, then you know automatically the charge on each one. Okay. All right, 28. Equipotential lines for some region of space are shown in the figure. All right, so want to know what's the electric field at point A. So what you can do is assume between 0 and 1 volt between the dotted lines that the electric field is uniform. So let's assume this is about 1.5 and that is about 0.75 volts, because that's about half a volt, that's 1 volt, that's about 0.75 volts, about halfway up. And that's about halfway between 1 and 2 meters. The electric field strength is measured as volts per meter, so we can just do 0.75 volts divided by 1.5 meters, okay? And but when we go to point B, we got to assume that the electric field here is uniform. So that's 1 volt divided by, and this is going to be 3.5 meters. So that's about half a meter. So those are your two electric field strengths between there. And that's, you'll do a lab where you figure this stuff out too. Okay, 29. A positive charge is moved from one point to another along an equipotential surface. The work required to move the charge is what? So if you have a, screenshot. If you have a mountain, for example, okay, and you walk around the mountain and you don't go up or down, the work you do would be mgh. But if you never change height in your gravitational field, then you're not going to do any work within the gravity. Of course, you'll be sweating because you'll be, walking around doing other things, but you won't. The gravitational field itself won't do any work because you don't have to fight gravity at all. This is the same thing if you move along an equipotential surface. The potential is the same all the way around, so the amount of work should be what? Okay, an equipotential surface must be, so remember we will have a surface, a charge like this, and it could be emanating electric fields, and remember equipotential lines are always whatever that is. What kind of term is that? 90 degrees. Is that parallel, tangent, equal, perpendicular, or inverse? All right, delete. And then 31, a parallel plate capacitor has a plate separation of 2.3 millimeters. If the material between the plates is air, what plate area is required to provide a capacitance of 1 picofarad? So we've got capacitance is epsilon naught A over D. All right, we've got a separation of 2.3 millimeters. It's air, so this kappa value is 1, so we don't worry about it. Plate area is what we need, and we got 1 picofarad. So you got 1 picofarad times D divided by epsilon naught. That's going to be the area required. Okay, and then 32. Explain why capacitance C depends neither on storage charge Q nor the potential difference V. And that is because C is epsilon naught A over D. Where in there is V or Q? Okay, delete. 33. A parallel plate capacitor has plates of this by that. The plates are separated by a piece of paper. What's the capacitance? The dielectric is 2.4. So now you've got C is equal to kappa the dielectric constant, epsilon naught A over D. A, they're trying to trick you. A is just 4.7 times 4.1 centimeters squared, okay? And D, you've got your separation there. Again, Wolfram alpha helps you keep track of all these units. And then 34, the last question, is what is the energy stored in a capacitor? Remember, energy in a capacitor is 1/2 CV squared. So that's easy, you can figure out what that is. And then the amount of charge, Q, is CV. Okay, done. Delete. All right, good luck, bye.